Okay, so this is going to be the third lecture on Riemann integral. Just avoid the music going behind. Just focus on my words. There's some sort of a function going on here. Okay. So apart from that, we had basically completed till theorems related to lower and upper Riemann sums, right? Okay. So now we move on to what we call a Riemann integral. Okay. Now we move on to what we call a Riemann integral. Clear? Riemann integral. So for some function, let's say f. Okay, so let f be a real valued bounded function. So let f be a real valued bounded function defined on some interval I equals to a comma b. Okay, now we have already defined the terms of LFP and UFP, right? So LFP, what was LFP? This is just sort of a recall. Okay, so what was LFP? LFP was the summation r equals to 1 to n delta r times, sorry, mr times delta r. Mr was the greatest lower bound of the interval IR, right? Where IR was the interval xr minus 1 to xr, where these elements belong to a set which we call partition, right? We have recalled this. Further, what was UFP? In a similar way, we have defined UFP as r equals to 1 to n capital MR delta. Capital MR was the LUB of the interval IR. Clear? This we already know. And then we have already studied the theorem related to lower Riemann sum and upper Riemann sum, right? Now, the first thing here is that we have studied this statement that where m is the GLB of the function over the complete interval, so m times b minus a is less than equals to LFP, which is less than equals to UFP, and which is less than equals to capital M times b minus a, where capital M is the LUB of the function over the complete interval. So from here we can obviously say that the lower Riemann sum and the upper Riemann sum are bounded functions, or are bounded rather, are bounded. Okay. So from here we reach the definition of what we call the lower integral, lower Riemann integral. Okay, lower integral. So what is the lower integral? So we define lower integral as a bar to b f dx, which is basically the LUB of all the lower sums, lower Riemann sums possible for all partitions possible of the interval I. Clear? Got it? Clear? In a similar way, we have also defined what is an upper integral. Okay? Upper integral is defined as a definite integral a to b bar f dx, and it is the greatest lower bound of all the upper Riemann sums for all partitions P of I. Clear? Got it? Now, when these two values exist, the upper integral and the lower integral, using these two values, we can define the integral, the Riemann integral of a particular function in some interval. So let us define that. So a real valued bounded function, f defined on a finite closed interval I equals to a to b is said to be Riemann integrable on the closed interval a comma b if integration a bar to b f dx is equals to integration a to b bar f dx. Clear? Clear? F dx. Okay, that is the lower integral equals the upper integral. Got it? Got it? And let this value be, say, let me write it as a value itself, and the value of this lower integral which equals the upper integral is called the Riemann integral, of f in AB, written as integration a to b fx dx. Okay, we can write these as fx dx also, or we can write this as f dx. So this is a short way of writing f dx. Okay, you can write it as fx dx also, nothing, no problem in that. So basically f is integrable on AB, then if f is integrable on AB, then the lower Riemann integral of the function equals the upper Riemann integral of the function, which equals the definite integral of the function within the limits AB. Got it? Clear? Clear? Okay. From here we get, so you people have understood this, what is a Riemann integral of a function over some interval. Clear? Okay. So from here, let's check a few results or a few theorems related to this lower and upper integral. For example, there's a very important result for lower and upper integral, that is that let f be a real valued bounded function defined on I equals to AB, then integral a bar to b fx dx equals to integral a to b bar fx dx. Clear? Clear? Okay. So let's check the proof of this particular theorem. Got it? Proof. Okay. Acha. Let you say you have two partitions. Okay, let us generalize the concept to take two partitions into consideration. Okay, so let P1 and P2 be two partitions of I, and we already know, we have already done this in the previous lecture, that LF P1 is less than equals to UF P2, right, for all Pi partitions of I. Clear? Got it? Now if the lower Riemann sum over some partition P1 is less than equals to the upper Riemann sum over some partition P2, then the greatest lower bound, then the least upper bound of this lower sum will also be less than equals to the upper sum of this function over the partition P2, right? So we can obviously write that this implies LUB of LF P1 for all Pi partitions of I is less than equals to UFP2, which implies the lower Riemann sum of the function is less than equals to UFP2, right? This much is clear. Now if this is less than UFP2, now see, basically what is happening here is that now UFP2, now what do we define as AB bar? So AB bar is the greatest lower bound, sorry, okay. Now what is this particular value? So this is the GLB of UFP for all P partitions, right, of I. So if FDX is less than equals to all the upper sums possible for any PI partition in the interval, then it is obvious that this is also less than this particular value, the greatest lower bound of all the partitions of all the upper sums of the function over all the partitions present in I. So from here we can obviously write this, right? A bar to B FDX is less than equals to A to B bar FDX. Clear? Got it? Got it? Okay. Now let's move on to some problems related to Riemann integration. Okay, let's check a few problems. Okay, so in this lecture we are gonna do some very basic problems. The next lecture onwards we are gonna move to some advanced level problems or some higher level problems. Okay. So let's check the first question. So here we take a linear function. Okay, here we take a linear function. So if fx equals to x, say x is in the interval 0, 1 and P is the partition 0, 1 by 3, 1 by 2, 2 by 3 and 1, okay, be a partition of the interval 0, 1, compute LFP and UFP. Okay, a very basic problem. Let's see. Okay, so you have taken the interval 0, acha, what are the sub intervals possible due to this partition? So let us write the sub intervals. So I1 can be written as 0 to 1 over 3. I2 is the sub interval 1 over 3 to 1 over 2. I3 is the sub interval 1 over 2 to 2 over 3, and I4 is the sub interval 2 over 3 to 1. Okay, so these four sub intervals are present. Now what we need to do is that we need to check the greatest lower bound and the least upper bound of the function in these intervals, right? So what is M1? Now see, since this is a linear function, this is a monotonically increasing function, so the value of this function in every sub interval increases starting from the lower bound till the upper bound. So the greatest lower bound of the function in each sub interval is basically the image of the function at the starting value, and the least upper bound will be the image of the function at the ending at the end point of the sub interval, right? So what is M1? M1 is 0. What is M2? M2 is 1 over 3. What is M3? M3 is 1 over 2. And what is M4? M4 is 2 over 3. Similarly, what is capital M1? 1 over 3. Capital M2 is 1 over 2. Capital M3 is 2 over 3. And capital M4 is 1. Then we need to find the length of each sub interval, right? So what is delta 1? Delta 1 is 1 over 3. Delta 2 is 1 over 2 minus 1 over 3, that is 1 over 6, right? What is delta 3? Delta 3 is 2 over 3 minus 1 over 2, okay? So it is 1 over 6 as well, right? 1 over 6, right? And what is this? So this is 1 over 3, right? 1 over 3. These are the lengths of the subinterval we have got, right? Right? Okay. So now if we find LFP, so LFP is basically the summation r equals to 1 to n mr delta r, that is equals to m1 delta 1 plus m2 delta 2 plus m3 delta 3 plus m4 delta 4, right, because n is 4 here. So m1 is 0, so we are not taking that particular value. M2 is 1 over 3 times 1 over 6 plus m3 is 1 over 2 times 1 over 6 plus 2 over 3 times 1 over 3, right? Right? So this is 9, 12 and this is 18. So we can take the LCM as 36. So this is 2, this is 3, 5 and this is 4, right? 4 2 is 8, 5 and 8, 13. 13 over 36 is your answer to LFP, okay? And in a similar way we need to find the UFP. So UFP is basically the summation r equals to 1 to 4 capital MR times delta r. So it is basically 1 over 3 times 1 over 3 plus 1 over 2 times 1 over 6 plus 2 over 3 times 1 over 6 plus 1 times 1 over 3. So this is coming out to be, so the LCM as 36 again, and this is 8. So this 9 and this is 9 and so 2 cancels 3, right? So this is 9. So 2 over 9 you have got. So this is 8, right? 36 8. Yeah. So plus this becomes 3 and this is 12. So this is 23 over 36. Clear? Got it? Got it? Okay. So we have checked how to find the LFP and UFP. Now we need to do some problem related to the concepts of upper integral, lower integral and the Riemann integral. Okay. So let's take this question into consideration. Show that fx equals to 2x plus 3 is integrable, fx equals to 2x plus 3 is integrable on the subinterval 2 comma 3 and the Riemann integration 2 to 3 f dx is equals to 8. Okay. So in this particular problem what we need to do is that we need to find LFP, UFP and the LUB of LFP, the GLB of UFP, and we need to compare them. If they are equal, then this function is Riemann integrable and the value of each of them is basically giving you the value of the Riemann integral, right? Okay. So for this particular problem we need to start with forming a partition of this particular interval. Okay. Now the whole problem, the solution to this problem basically lies in forming the partition itself. If you can form the proper partition, you will be able to solve this particular problem. So in this case, when you are having a polynomial, okay, when you are having a polynomial function, then what we do is that we choose a specific type of partition to solve these problems. Okay. For example, what we do is that if I talk very generally, then we break this particular partition. Suppose you are given this particular interval. Suppose you are given an interval a comma b. What we do is that we start with the value of a and then we keep on increasing the elements of the partition by h, okay, till we reach nh. Okay, and this h is equals to b minus a over n. H is equals to b minus a over n. Is it clear? Is it clear? Got it? Got it? Okay. Now let's do the same thing in this particular case. Okay, so I'm rubbing this portion. We will be keeping the value of n, because we basically what we are doing is that we are forming, we are structuring a general form of a partition. We are structuring a general form of a partition because in case of finding the upper integral and the lower integral, we have already known the statement that it must happen for all possible partitions of the function, right? So we need to generalize the structure of the partition, and for that reason we will be keeping the value of n as a variable here, because that particular value of n will generalize the structure of the partition to show that there exist many more partitions of the same form, right? And that particular variable n will help us also achieve the values of the GLB and the LUB. Okay, so what we can do basically is that, so we can form the partition. So let P equals to 2 plus B minus A by n, right? So 1 by n, then 2 plus 2 by n, and so on till you have 2 plus n upon n, which is equals to 3. Okay, so we have formed the partition successfully, and from here what can we write as the rth subinterval? So it is basically 2 plus, so see, if you have taken this in, this as I1, okay, so I1 is r minus 1 over n to r over n. Got it? And what is the length of each subinterval? Equal length 1 over n. Clear? 1 over n. Got it? Got it. Now see, since this is a linear function, this is a monotonically increasing function. Okay, so for every interval, what is the GLB? Sorry, what is the GLB for every interval? So it is basically the image of this particular function at the starting value, right? So it is 2 times 2 plus r minus 1 over n plus 3, which is, if you solve it, so this is 4 plus 2r minus 2 by n plus 3, which is 7 plus 2r minus 2 by n. Got it? In a similar way, what will be the LUB of the function at each interval? It will be the image of the function at the end point of the interval, right? So it is 2 times 2 plus r over n plus 3, which is 7 plus 2 times r over n. So now we have got the values of MR, and we have basically got the values of the small MR and the larger MR, right? Now we need to form the LFP. So what is going to be LFP? So LFP is the summation r equals to 1 to n of small mr, that is 7 plus 2 upon n into r minus 1, right, times 1 over n, So we can, first of all, what we can do is that, so see this becomes summation r equals to 1 to n 7 by n plus this becomes 2 by n, we can take 2 by n squared, we can take outside because it is constant in this case, r equals to 1 to n summation r minus 1, right. In this case also we can take 7 by n outside, and what is the summation of 1 from 1 to n? It is n itself, right, and this is 2 plus 2 by n square. So we can write this r minus 1 as 0 plus 1 plus 2 till we have reached n minus 1, as simple as that, right. So this is 7 plus 2 over n square times n into n minus 1 by 2. So this 2 cancels out, this cancels out, so you have 7 plus n minus 1 by n, which you can write as 7 plus 1 minus 1 by n, right, which is equals to 8 minus 1 by n. Now when you have already got the LFP in this form, the LUB of LFP for all partitions P in I, you can find it out using limit n tends to infinity of LFP, which is limit n tends to infinity 8 minus 1 by n, which is equals to 8. In the exact similar way, we need to find out UFP. So UFP is the summation r equals to 1 to n 7 plus 2r by n times 1 by n. So it comes out to be 7 by n times r, summation r equals to 1 to n time of 1 plus 2 by n square into summation r equals to 1 to n times r of r. Okay, so this is 7 plus 2 over n square. Summation of r from 1 to n is n into n plus 1 by 2. So this cancels out. This comes out to be 7 plus 1 plus 1 by n, which is 8 plus 1 by n. And to find the GLB of the upper sum for all partitions P in I, we can take limit n tends to infinity of the UFP, which is limit n tends to infinity of this value 1 over n 0, so it comes out to be 8. Therefore, now what is this? This is the upper Riemann sum and the previous value is the lower Riemann sum. So therefore, we have got there the lower Riemann integral of f dx equals a to b bar f dx equals to 8. That implies integration. Now what is a? A is basically, okay, let me write it as the value itself. Okay, so 2 to 3. So from these two values we get the Riemann integral 2 to 3 of f dx equals to 8. Clear? So let this lecture be up till this much, guys. In the next lecture we will solve some more problems and then we will move on to further concepts. Okay, so meet you guys in the